Okay, so let's look at some questions under this topic, which is units and measurements. And question one or part one is saying conversion of units. Conversion of units here. And there are two questions, question one and question two. Question one reads, a fathom is a unit of length, usually reserved for measuring the depth of water. A fathom is approximately 6 foot in length. Take the distance from Earth to the Moon to be 250,000 miles and use the given approximation to find the distance in fathoms. We approximate the distance from Earth to the Moon to be 250,000 miles. Then our goal is to measure this distance, which means we convert this distance that is in miles to fathom, which is this guy here. So how can we approach this question first? We can find the conversion factor of miles to feet. Since they've told us to say a fathom is approximately 6 foot long, so we can find a conversion factor which can give us this number, which is 250,000 miles, into foot or feet. Okay, so the conversion factor of a mile to feet is 1 mile. Okay, let me just go to my blank board. So we have 1 fathom. They've told us to say 1 fathom. So 1 fathom is equal to 6 feet like this. And our goal is to convert 250,000 miles to fathom. Like that. Okay, so what can we do from here? We can start by converting these 200 miles into feet like this. And we have a conversion factor to say 1 mile is equal to 5,280 feet. So using this, we can convert the miles into feet by multiplying these guys. So I'll say 250 miles, or I mean 250,000 miles multiplied by 50, 5280. And this will give us 200. Okay, so it is going to give us 1,320,000,000 like this. So these are the feet. From the Earth to the Moon, we have 1,320,000,000 feet. So we can now convert from these feet into fathoms. We've been told to say 1 fathom is equal to 6 feet. So what are we going to do? We're going to divide this number by 6. And what are we going to get? We're going to get a distance which is equal to 220 million, like that, fathoms. So that means the distance from the Earth to the Moon is equal to 220 million in fathoms. Okay, so that was question one. We can go to the second question. The second question is saying a car is traveling at a speed of 38 meters per second on an interstate highway where the speed limit is 75 miles per hour. Is the driver exceeding the speed limit? Justify your answer. Is the driver exceeding the speed limit? Justify your answer. That is part A. So how are we going to justify our answer, whether the driver is exceeding the speed limit or not? First, we're supposed to convert this 75 miles per hour. Let's convert it into meters per second, so that we compare these meters per second that we're going to get from this conversion and the speed at which this driver is moving. If the speed is more than this, that means the driver is he's driving under speed limit. But if this guy is smaller than the 38 meters per second, that means the driver is exceeding the speed limit. So let's convert 75 miles per hour into meters per second. Okay, so we have driver's speed, which is equal to 75 miles per hour. Also, we have the speed limit, the driver's speed is 38 meters per second. 38 meters per second, like that. Okay, so uh, let's bring down the conversion. We're going to convert these into meters per second. And one thing we have to understand is that if the conversion factor, the direct conversion factor from mile to meters is 1 mile. Let me write something sensible. This looks disorganized. 1 mile is equal to 1609.34 meters. Okay, so using this conversion factor, we can convert our speed limit to meters per second. So what are we going to do? Say 75 miles per hour multiplied by 1609.34 meters over 1 mile multiplied by 1 hour, which is equal to 3600 seconds. Okay, so the hour and the hour cancels out. The mile and the mile cancels out. So 75 multiplied by 1609.34 multiplied by 1 divided by 3600 seconds. So we are supposed to get the speed limit. Speed limit that is approximately 33.5 meters per second. Let me just count to check it again. 75 multiplied by 1609. 1609.34. That divided by 3600. Okay, so I'm getting 33.53. Okay, which is the same as 33.5 meters per second. So you can see to say the speed limit of which is indicated on the street is lower than the driver's speed. That means the driver has exceeded the speed limit, since the speed limit is way lower than the driver's speed. So say the driver exceeded the speed limit. Like that. Okay. Okay, the question was saying, is the driver exceeding the speed limit? Yes, justify your answer. We've just justified it. Okay, convert 200 grams per square centimeter to kg per square meter. Convert 200 grams per square centimeters to kg per square meter. Okay, so we have 200 grams per square centimeters to kg per square meter, like that. So what do we do? Remember, we just have to, if you're dealing with squares or units that have powers, the only thing you're supposed to do is to introduce the same power to your conversion factor. And in each case, you should make sure you introduce the square to the conversion factor that is having that same power, not everything else. No. So I'll say my 200 grams over square centimeters multiplied by, we are converting grams to kilograms. So what are we going to have? We're going to have 1 kilogram, which is equal to what? Which is equal to 1000 grams multiplied by, we have centimeters to meters. So we're going to say multiplied by, let me say 1 meter here, which is equal to 100 centimeters. Okay, like that. So the centimeter is the one which is having a square power. So we're going to introduce our power to that conversion factor. So we are going to have this gram and that gram will go. So we're going to have 200 kg on top, 200 kg over square centimeters multiplied by, I'll introduce, okay, so let me say 1000 here. Let's multiply in advance. Then I'll distribute this power to both the numerator and the denominator there. So I'm going to have 100 square centimeter square over 1 meter square, like that. Okay. 200 kilograms over 100 or 1000 centimeters squared multiplied by 100 squared. This should give us 10,000. Okay, so we're going to have multiplied by 10,000 centimeters squared over 1 meter squared. So the centimeter squared and the centimeter squared will cancel out. We're going to remain with 200 multiplied by 10,000 to give me 2 million over, this is kg, over 1000 meter squared. Okay, it's now meter squared since the centimeter square has been cancelled out. So 200 or 2 million divided by 1000. I'm getting a final answer which is equal to 2000 kg per meter squared, like that. Okay, so that is the final answer for question 1. Part B, we can move on to the next question. Question 2, part B. We can now go to these questions that are under dimension analysis. Okay, so we have question 3, which is saying determine whether the following two equations are correct or wrong. There's something wrong with the statement. Determine whether the following two equations are correct or wrong. So these are the equations that are supposed to check. This one and this one. So we have equation A, which is saying mass times acceleration is equal to v squared. Mass times acceleration is equal to v squared. So what do? We're going to use dimension analysis on these equations. On both sides, check the units. If they are similar, that means the equation is dimensionally constant, hence it's correct. If the two sides have different units of equation, that means the equation is dimensionally inconsistent and therefore it cannot be correct. So let's go for A. She's saying MA is equal to V squared. Okay, question 3. A saying MA is equal to V squared. So MA, this is mass multiplied by acceleration. So I'll say mass M multiplied by acceleration. And what is acceleration? Acceleration is equal to meter. So for meter, let me use L for length. Or for mass, let me just use kg to simplify everything. Let me use units. Okay, I don't know what is going on. Let me just... Okay, let me just start from here. I'll say this is equal to what? It is equal to mass. I'll use kg being multiplied to acceleration, which acceleration is meters per second squared. And this they are saying is equal to velocity squared, of which velocity is just meters per second, but in this case it's squared. So what are we going to have? We're going to have kg meter per second, or second squared rather. This is a 2 being equal to meter squared second, like that. So in this case, we can simplify this equation further. I'm sure you can see. If we want maybe to cancel something from both sides of the equation, we can just cancel out the second power -2 and the second power -2 there, and we're going to have kg multiplied by mass. This is equal to meter squared, of which this is not correct. The two sides of our equation are not correct. Hence, this equation is wrong. Even from here, in case your lecturer doesn't want you to reach this part, this final part, even just by reaching that step, you can tell to say the two sides of the equation are not the same. Hence, the equation is not dimensionally consistent. Hence, it's wrong. Okay, we look at part B. Part B is saying x is equal to v initial multiplied by t plus half at squared. X, which is displacement, is equal to velocity multiplied by t plus half at squared. Okay, so that is part B. 3B. 3B is saying x is equal to v initial, so I'll just use u for initial velocity, ut plus half at squared, like this. Okay, so let's check if the equation is dimensionally consistent by checking the units on the left and the right hand side. So x is for displacement, of which displacement is measured in meters. So I'll say meters on the left hand side. Then u is meter per second multiplied by second, which is for time, plus, remember this is dimension analysis, so we ignore all the constants. We just deal with the units of measurements. Let's leave the constant there. So acceleration will be plus meter over s power 2. This also multiplied by what? Multiplied by s squared, which is time squared like this. Okay, so what are we going to have here? We're going to have the meter is equal to, from the multiplication that is taking place here, you can tell to say this is a denominator, S, and if you're multiplying like that, that can go. So we remain with M, uh, plus, we also have M here over S squared, multiplied by S squared. So this S squared actually can cancel out with that S. Then we are going to remain with the M plus M. Okay, and since this is dimension analysis, you can add these two. You are going to get M is equal to 2M. But since in dimension analysis, we don't deal with the coefficients, but rather the variables, which is only the units of measurements and not the constants, you can see to say we are going to remain with exactly M is equal to M. And that is dimensionally consistent on both the left and right-hand side of the equation. Hence, this is correct. Okay, so that was question 3. We can now move to question 4. Okay, so question 4 is saying, given the units of force as kg meter per second squared, write a simple equation relating a constant force F exerted on an object, an interval of time t during which the force is applied, and the resulting momentum of the object P. Given the units of force as kg meter per second squared, write a simple equation relating a constant force F exerted on the object, an interval of time t during which the force is applied, and the resulting momentum of the object P. So, what are we going to do in this case? Let's go to our board. Okay, so this is question 4. And we've been asked to say we should give out a simple equation that relates the force, the constant force applied, momentum, and time. So this is what we've been given. We have to relate force, momentum, and time like that. So a simple equation that relates or that is relating force, time, and momentum is this equation. We say momentum is equal to a constant force applied multiplied by time like that. Even by checking these units, you can tell to say this equation is dimensionally correct, because if you want to define momentum, you will say momentum is a what is momentum? Or this force here is the rate change or the rate change of momentum. This constant force that is applied is equal to rate change of momentum. So in short, this equation can also be uh, rewritten as F, which is force. This is equal to change in momentum over a certain period of time. So this is the equation using Newton's second law. That's how you can, or that's the simplest equation you can denote or you can deduce from the three quantities that we've been given. Because this equation is a simplified form of Newton's second law of motion, and Newton's second law of motion states to say the force is equal to the rate change in momentum. So that is the simple equation that we can deduce from the three physical quantities that have been given. Okay. The rate change of momentum is directly proportional to the force or to the constant force applied multiplied by time taken or the time interval. So this is the equation here. Let me write it clearly. Let's say P, which is momentum, is equal to force multiplied by time, like that. Okay, so go to the next question. The velocity of a particle varies with time t according to the relation v is equal to at squared plus bt plus c. Find the dimensions of a, b, and c. Find the dimensions of a, b, and c. So what are we going to do here? This question is not very difficult. There's just one thing we're supposed to understand. When you've been given an equation under dimensional analysis, you've been given an equation which is like this. And you say V is equal to AT squared plus BT plus C. Uh, the dimensions of A and B and C. Here, A is a constant, B is a constant, and C is a constant. So how do you find the dimensions of these? Actually, this guy on the left-hand side, V, is supposed to be equal to these guys individually. So V is equal to AT squared, V is equal to BT, and V is equal to C. That's how dimensional analysis works, or that's how formulas work. If you've been given such a formula, V is supposed to be equal to AT squared individually, V is supposed to be equal to BT individually, and V is supposed to be equal to what? To C. So that has already simplified our equation, and we are going to use this in order for us to find the what? What are we finding? The dimensions of A, B, and C. Okay, so that is question 5. Question 5, we've been given to say V is equal to AT squared plus BT plus C. So I've said in order for us to find the dimensions of A, B, and C, what are we going to say? We're going to say V is equal to AT squared, V is equal to BT, and V is equal to what? Is equal to C, like that. So what is the dimension of V, which is velocity on the left-hand side, like that? Velocity is equal to L, which is distance, T to the power minus 1. So LT to the, here I'm not using uh, base quantities or base units. I'm using the dimensions themselves. For length, I'm just using L and not the units. For T, for time, I've just used T like that. So this is equal to A and T, we have T squared like that. The second one, we have V, which is LT to the power minus 1 being equal to B multiplied by T. Okay, so the last one, we have LT to the power minus 1 is equal to C. So you can tell to say the last one for C, it has already given us the dimensions for C. For this one, we're going to make B the subject to the formula. Hence, what are we going to do? We're going to say this will be equal to what? Like this, we have B is equal to LT to the power minus 1 over T. Like this. We are dividing by this T. Okay, and this is going to give us what? This should give us B being equal to LT to the power minus 2. So B is equal to LT to the power minus 2, like that. Okay, then this one, we are going to make T or A the subject of the formula. So we should be able to get A is equal to LT to the power minus 1 divided by over T squared. So what are we going to have? We're going to have A being equal to LT to the power minus 3. Something like this. So let me write them down here clearly. I'll say the dimensions for A, it's LT to the power minus 3. The dimensions for B, this is LT to the power minus 2. And the dimensions for C, that is LT to the power minus 1, like that. Hence, we've shown the dimensions for A, B, and C. Okay, so let's move to the next question. Okay, so question 6 is saying the kinetic energy Ke has units kg meter squared per second squared. It can be written in terms of the momentum P and mass M as Ke is equal to P squared over 2M. Determine the proper units of momentum. Determine the proper units of momentum. So if we go to our blank board, we've been given to say the units of Ke. The units of Ke are kg meter squared second squared, like that. Okay, so it can be written in terms of momentum and mass as Ke is equal to momentum squared over 2m, of which 2 here is a constant, as you can see. So to determine the proper units of K, what are we going to do? We're going to use the units of these guys that we've been given here. So what is the SI unit for momentum? That is what we are trying to look for here. So what are we going to do? Let's plug what we know into this same formula that we have. But remember, we have to make momentum the subject of our formula. Okay, so what are we going to do? We're going to say like that, I cross multiply. I'm going to get P squared is equal to Ke multiplied by 2m, like that. Okay, and I can put my 2m in brackets. Then I'm going to introduce this on both sides of my equation. I'm going to remain with P is equal to Ke, then in brackets, I'm multiplying Ke by 2m, like this. Okay, so we can now plug in the units that we know. We'll say P is equal to the root of the roots for Ke. They've told us to say this is kg meter squared per second squared, like that. Okay, then we are multiplying this by what? Let me put it in brackets like this. We're multiplying this by 2m. And what is m? This is 1 kg, like this. Okay, so this is what I'm going to have. Okay, I put a dot there just to indicate that I'm multiplying. This will be equal to what? I can bring out the 2. In short, I could have even ignored it in the beginning before even starting to plug it under the square root, because we know in dimensional analysis we are only dealing with variables. So we neglect the integer. Okay, so I'll say my P is equal to what? P is equal to kg multiplied by kg there. I'm going to have kg squared. Okay, then I have the meter squared and the second the power minus 2 like that. Or if I want, I can still bring it down as a denominator. Okay, over s squared like that. Okay, so this is what I have. And where can I go with this from here? I'm sure we can tell to say if everything is squared here, I can just write everything in brackets, then I put a square outside. So I'll say momentum is equal to kg, like that, multiplied by meter over second. I plug this into the brackets. I put the square outside because everything is squared, the numerator and the denominator. So if there is a square and the square root sign here, that means this guy is automatically cancel out like that. And that means I'm going to remain with what? I'm going to remain with P, which is momentum, being equal to kg meter per second. So those are the proper units of P. So thank you very much for watching this video. Kindly like, subscribe, comment, share the video for more content like this, and register with us for the remaining parts of the assignment. The solutions are on our drive on our website, so they'll be accessed by those who register. So kindly register with us and have it the easy way. Thank you very much, guys. Until next time, stay blessed.